lies between a conductor and an insulator. We also saw semiconductors to be materials that partially conduct electricity on condition. And what is this condition? On condition that there is applied heat or increased temperature or increased temperature, or when there is a strong electric and magnetic fields, conductors also conduct. So these are the conditions on which must actually prevail for semiconductors to conduct. And examples of semiconductors, we made mention of silicon. Silicon is one. Two examples of semiconductors. Here is silicon,
Germanium.
Germanium,
Arsenic.
For arsenic, when you are pronouncing it, be careful, else you'll be talking about arsenal. Arsenic. So semiconductors are the metalloids on your periodic table. Okay. So they will conduct on condition that there is applied heat or there is strong electric and magnetic field. In fact, semiconductors have a lot of applications. In physics, when we talk about applications, we are talking about uses. Semiconductors are used or applied in a lot of fields, especially in communication or information technology. And it is also greatly used in electronics, in the electronic world. So let's look at some applications of semiconductors. Semiconductors are used in transistors. Electronic components are basically made of semiconductors. So electronic components such as transistors, microprocessors, oh, the network, microprocessors, diodes, etc. are all embodiments of semiconductor or semiconductors. Okay, class, what do we use transistors for? If you have any idea, can you please share with us? So we are saying that semiconductor applications can be seen in communication, electronics, okay, medical field, a lot. One of it is transistors, microprocessors, diodes. Can you tell me about the uses or the usage of transistor. What do we use transistor for? Karim, Zainab.
Yeah. These transistors can be used as amplifiers to amplify weak signals.
So they can be used for amplification. Can you explain this? Can you explain what we mean by amplification? Use typical.
Like when the signal is weak, they use the amplifiers to make it stronger.
Can you give a device, a specific device which amplifies weak signal? Okay, I'm sure you know, but the connection. Yes, so thanks, Zainab, thanks for the contribution. Please, can I hear from any one of you? Yes, if you have raised up your hand, please go ahead. If your hand is up, please go ahead.
They are used to turn off, they are used to switch on and switch off some electrical devices.
Yes, you are also talking about for switching purposes, which is true. But I want us to understand what we mean by it's being used to amplify signals. Okay, you see, we all know about amplifiers. The amplifier used in Saki.
I wanted to explain the amplification.
Yeah, just amplify it. Go ahead.
You said, please, it strengthens the signal or the electric current.
Okay. Okay, so that is true. The obvious example is that when we go for any gathering, whether in a church, in a mosque, or any social gathering, and there are a lot of people, because the voice or the sound from our voice cannot reach out to the number of people or the space, or our voice is overcome by the noises or nuances around, we go for microphone and then speak into it. Okay, so when you speak into a microphone, the amplifier, there is something to which the microphone is connected to. That is the amplifier. It would increase your voice or the sound so that it can be heard by the people around. This is a clear example of amplification of sound. So the amplifier which we have in our homes, churches, mosque, and other gatherings are all embodiment of transistors. There are transistors within the amplifier which does this increase this gains. Apart from amplification of voices, sometimes we also have voltage regulation. Okay, so smaller voltage to be increased to a larger voltage. That is also a form of amplification, which is also done by transistors. So that explains the amplification as the purpose of a transistor. Please, is there any question? All right, then let's look at switching. What do we mean by for switching purposes? We are saying that transistors are used for switching. What do we mean? Can we give a practical example to understand this? Okay, so you see, look at that the traffic lights. which control traffic on our roads. There is nobody in the office which controls the traffic light, that green light come on, red come, yellow. No, nobody controls it. The control is done by transistors. So the transistor switches, that green switch, yellow off, red off, red switch on, green go off. So this switching on and off of the traffic lights, as an example, is done by transistors. So that also explains the switching aspect of the function of transistor. Please, can you hear me?
Yes.
Yes, please.
Okay. Another switching application or function as done by transistors is that, you see, when you go to we are billboards, this modern LED billboards, which is displayed in town on giant screens. The switching, this will come on, this will go, okay, this will go off, and even the latest screens, televisions, LED, okay, televisions and all that are controlled by transistors. Switching, this must come on, this must go off. So the control, when you go to airports, okay, there are a series of information given to you on the screen. Okay, flight to New York will leave at this time, another one will come. This switching on and off of information given by light emitting diodes are all controlled by transistors. So these are the two explanation to the switching parts or function of transistors. So we say transistors are used for amplification and for switching of signal. Okay, so lesser signal can be increased, the gain can be increased, so we have a larger output. Okay, and control of current. Switching on this will go off displays or light emitting diode displays, and so these are all switching, which is done by transistors, and they are made of semiconductors. In fact, the speed of laptops and computers are actually as a result of the number of transistors that are used in building it up. So if you have a device, electronic gadget whose speed is so much, then it means they contain more transistors. The speed is determined by the number of transistors used. Now, diodes, another gadget, which is also an embodiment of semiconductor diodes. Can somebody tell us what a diode is? A diode. Light emitting diode. Frank. Photodiodes.
Sir,
Frank.
please you explain what a light emitting diode is or what a normal diode is?
What a diode? What is a diode? Oh, Frank. Okay, let me go to a different. Zainab, what is a diode?
Sir, please, a diode is an electronic component that allows current to flow in one direction.
Good. Electronic
While
component that
blocking it in the other.
Thank you. More for better and further particulars. Yes. So a diode is an electronic gadget that allows current, okay, to flow in only one direction. Diode is used for rectification. So we use diode for rectification. Used for rectification. And rectification is the process of converting AC to DC. Process of converting AC to DC. AC is alternating current. DC is direct current. So when you have alternating current from Akosombo, from the generator in our homes, from bigger plants, in offices, homes, you can convert it to direct current. This conversion is done by the use of diodes, and this process is known as rectification. Okay. Now, we make use of the product of rectification all the time. All devices that work or operate on batteries, whether dry cells or rechargeable cells, make use of DC. So batteries, whether dry cells, wet cells, or rechargeable cells, produce direct current. Okay. Now, devices that use batteries, laptop. The laptop uses battery. So there is a rechargeable battery. Some desktop computers use that. Our mobile phones use rechargeable battery. Please help me. I've given you 3. Laptop, from desktop computers, mobile phones, devices that use batteries. Yes? I'm waiting. Help me.
Headsets.
Headset. Some headset. Yes. Some power bank. Hands-free devices. Some torchlight. Yes. All use rechargeable batteries. You see, look at our mobile phone, for instance. When your battery level goes down and you connect it to the main switch or the socket in our homes, all that you are saying is that let the AC, there is a component in your charger head which converts the alternating current from the sockets to DC. The DC is what charges the battery. All batteries, rechargeable batteries, are done by direct current. We don't use AC to charge batteries. We use DC. We use a DC to charge batteries. So when you plug your laptop to the socket outlet, when you plug your mobile phone, okay, and desktop and all these devices all that you are saying, they have chargers. Within the charger head, there are diodes that are in there which convert the AC to DC. Okay, so typically The socket outlet in our homes gives us a voltage of 210 to 240 volts. Now our mobile phone batteries only require about 4 volts to 5 volts DC to charge. So when you plug your mobile phone to the socket, your mobile phone needs something small, around 4 to 5, but you are giving it a larger from 210 to 240. Okay, so it is like you need small amount of food, but you are being given a lot. If there is no redeemer or somebody to mediate, you can burst up because you need small and you are being given more. So the charger head has rectifiers. Or first there is a transformer. So your mobile phone chargers have a step-down transformer. There's a step-down transformer which converts the 240 volts to 4 volts. And then the diodes also take over to convert the 4 volts, 5 volts AC to 4 volts, 5 volts DC. So that is what happened in all chargers, being it mobile phones, laptops, and so on and so forth. Okay, so the rectification aspect is done by diodes, which are actually made of semiconductors, but the stepping down is done by transformer. So transformers are used for purposes of stepping down and stepping up alternating voltages. Please, is there any question? Is there any question? So these are some of the uses of semiconductors. Then let's look at transducers. Transducers, on the other hand. Transducers are actually used for changing one form of energy to another. Transducers convert one form of energy to another form of energy. Okay. I'm coming. Let me take attendance and get back to you. Daniel, please mute yourself. Daniel. Okay. So transducers, on the other hand, convert one form of energy to another. Example, the microphone the microphone converts sound energy to electrical energy. So the microphone is a form of a transducer. Then digital thermometers. Digital thermometers are also a form of transducer because they convert thermal energy to electrical energy to be recorded. Then some pressure sensors are also transducers. So basically, transducers convert one form of energy to another form of energy. An example is what I've indicated here. So that's the difference between transducer and transducers are also embodiments of semiconductor material. Okay, transducers can also function even as for amplification of voltages, smaller voltage to larger voltage and the other way around. So transducers are also made of semiconductor material. Okay, so that's the difference between applications of semiconductors and transducers. Let's quickly look at the types of semiconductors. Types of semiconductors. Then we quickly look at atomic physics. We have two main types of semiconductors. We have one, intrinsic or pure semiconductor, intrinsic or pure semiconductor, and two, extrinsic or impure semiconductor. So Janelle, can you hear me? Janelle is not here. Blessing. Hey. So we have the intrinsic and extrinsic semiconductor. What we mean by intrinsic semiconductor? Intrinsic semiconductor is a kind of semiconductor that is made up of pure semiconductor atoms. So intrinsic semiconductor is made of pure atoms of one semiconductor material. So what are we saying? What we mean is that An example of semiconductor, we spoke about silicon. Okay, so for intrinsic semiconductor, here we are talking about silicon atoms, 100% silicon atoms that are covalently bonded to form that silicon crystal. So here we have 100% silicon atoms that are covalently bonded to form this semiconductor material. So it is pure because we have pure 100% atoms of that same element or material forming it. So silicon is an example of an intrinsic semiconductor. If it's germanium, we have pure germanium atoms that are covalently bonded to form this material germanium. Yasmin and Co, can you hear me?
Yes, please.
Okay. So here we have 100% germanium atoms, 100% silicon atoms forming this semiconductor material. And if we have something like this, we call it as an intrinsic semiconductor, meaning made up of 100% silicon or germanium atoms forming the crystal structure of that material. Now, in an intrinsic semiconductor, we will later on go deeper. But for the meantime, I'll just talk about surface, and when there is the need for us to go deeper, we'll do that later. The conductivity or the conductivity level of an intrinsic semiconductor isn't good. So practically, we do not use intrinsic semiconductor in actually making transistors or diodes and so on and so forth. So for application purposes, we do not use intrinsic semiconductor. Why? Because their level of conductivity is so small. Augustine, are you there?
Yes, please.
Augustine, why am I saying that in application-wise, we don't use intrinsic semiconductor? What explanation did I give to that? That in practical applications, we don't use intrinsic semiconductor. And what's the reason?
Because they are too small.
The level of conductivity of intrinsic semiconductors is so small. Okay, it's so small that we don't use it for any practical purpose. I'm coming now. I'll get back to you. But may year class, my maybe I'm in fair. All right. So practically, that's it. We don't use it because of the level of conductivity they give us. Very, very small. But practically, what we use extrinsic semiconductor. So what is an extrinsic semiconductor? We have extrinsic semiconductor or impure or impure. Why do we call it as impure? You see, because the conductivity level of a pure state semiconductor is very, very small, we try to improve its conductivity. How do we improve the conductivity of an intrinsic semiconductor? We improve the conductivity of an intrinsic semiconductor by a process known as doping. So the conductivity of an intrinsic semiconductor is improved by the process known as doping. Say it after me, doping.
Doping.
Again,
Doping.
doping. Now, doping is similar to giving medicine to perform a certain function. So in athletics have anti-doping board. Athletics and sporting activities have anti-doping board. What is their function? They want to ensure that all athletes or sportsmen compete at their natural level or natural strength. And so before any athlete or sports person partake in an event, the blood sample of the athlete, the urine sample must be examined. Why do they examine it? To ensure that they don't use any substance which would improve their natural performance, meaning they don't cheat somebody. Okay, some people can decide to go for medicine which would give them so much energy, even to the extent that when they are running, they will not get tired. When you do that, it's a cheat. So there is a doping board which does this investigation to ensure that athletes compete at their natural strength. And when they find out that athletes use medicine to improve their performance, they will be banned from sports. Just recently, if you are a follower of football, Paul Pogba, former Manchester United player, was banned for using a certain medicine which they think would improve his performance than his natural ability. And so to them, Pogba had cheated for years. And so when they saw that sample of medicine in his blood or urine, Pogba had to be banned for a whole year. So this doping in semiconductors is similar to doping in athletics. Okay, we are doping to improve the conductivity of an intrinsic semiconductor, which cannot be used for any purpose naturally. So how do they do that? Please, just a minute to quickly connect my charger, please. Okay. So the conductivity level of an intrinsic semiconductor is improved by introducing other atoms that are different from the natural atoms of a particular semiconductor. So it is done by this introduction of either a pentavalent or a trivalent. These are just fanciful words, but a pentavalent is just any atom with 5 electrons in its valence shell. So a pentavalent has 5 electrons in its valence shell. Okay, then they can also improve the conductivity by introducing a trivalent. A trivalent has 3 electrons in its valence shell. An example of a pentavalent, we can, please, can you give me an example of a pentavalent? Any example of a pentavalent? Gideon. Phosphorus. Yes, phosphorus. Phosphorus, 1, 2. Just give me nitrogen, good. Then the doping, we can improve the conductivity by introducing a trivalent. Example, 2 examples of trivalent.
Aluminium.
Come again.
Aluminium.
Aluminium, yes.
Boron.
Boron, yes. So in introducing a pentavalent, okay, when you introduce a pentavalent, it creates extra electrons. So when you introduce a pentavalent in place of one of the silicon atoms, okay, because we don't have 100% either a pentavalent or trivalent, but in this case, because we don't have 100% silicon atoms, that is why we call this as impure. Impure because we don't have 100% atoms of that semiconductor material, but we have other atoms as well. And so that makes it impure. So extrinsic semiconductors are also known as impure semiconductors just because it is made up of other atoms. So that makes it impure. So when you introduce a pentavalent or trivalent, it makes it an impure or extrinsic semiconductor. And the extrinsic semiconductors, we have 2 main types. We have the N-type. N means negative. N-type extrinsic semiconductor, and P-type. The P here means positive. P-type extrinsic semiconductors. How they are actually obtained, for now we wouldn't go into this. We'll discuss that later, okay? But these are the types of semiconductors. We have 2 main types: intrinsic semiconductors, which is also known as pure semiconductors, and we have extrinsic semiconductor, which is also known as an impure semiconductor. Then when you pick the extrinsic, we have the N-type and the P-type. Don't forget, we obtain the extrinsic semiconductor through a process known as doping. And doping is the process of introducing atoms, either a pentavalent or trivalent, okay, material in order to improve conductivity of an intrinsic semiconductor. Please, if you have any question, quickly ask. If you have any question.
So this come again on the doping.
Doping is a process of introducing an impurity. Process of introducing an impurity. The impurity refers to either the pentavalent or the trivalent. Introducing impurity into the crystal structure of an intrinsic semiconductor with the aim of improving conductivity. So doping is the process of introducing an impurity into the crystal structure of an intrinsic or a pure semiconductor in order to improve conductivity. Please, are we okay?
So please, can you repeat it again?
Can I?
Repeat it again.
Okay. I said doping is a process of introducing an impurity. Process of introducing an impurity into the crystal structure of an intrinsic semiconductor. Introducing impurity into the crystal structure of an intrinsic semiconductor in order to improve conductivity. So basically, all that we are saying is that doping is done to improve conductivity. That is the idea behind doping. Okay, so we dope by introducing a pentavalent or a trivalent. When you introduce a pentavalent, or when you dope with a pentavalent, it gives you, or it produces, an N-type semiconductor. N-type semiconductor. Because extra electrons will be produced. Then if you dope using a trivalent, Michelle, are you there? If you dope using a trivalent, it gives you a p-type extrinsic semiconductor. A p-type extrinsic semiconductor, because holes or positive charges will be produced. Holes or positive charges will be produced. Please, if you have any question here, quickly ask. Frank.
Yeah.
Mm-hmm.
Does it mean that the group 5 elements in the periodic table, they are all N-type?
You see, group 5 elements, okay, have 5 electrons in their outermost shell, but we don't often use all of them. We often use phosphorus for this purpose, but you can actually dope with any pentavalent. And when you when you dope it with, when you dope a pure silicon with a pentavalent, yes, it will give you N-type extrinsic semiconductor, because the majority charge carriers there will be electrons. There are some further explanation I need to give, but because there is a level to which you must know, that's why I'm not going into details. All right.
Okay, sir.
All right. Please, have you exhausted your questions?
So it means that under the N and the P type, they have a specific element, like you have only one element, or
Oh no, we don't have one. As I said, we can use phosphorus. You can use, but you see, nitrogen, for instance, is a gas, and you cannot use gas for this kind of physical purpose. That is why. Okay.
okay, sir.
But you can use other solids that can actually be handled and be introduced into the crystal structure.
Okay. Thanks, sir.
Welcome. Saki and Co, can I move on?
Yes, please.
All right. The ladies are quiet too. Ashima, you are not talking.
Yes, please, I understand.
Okay. All right. Then let's look at the atomic model. So we discussed Rutherford's model yesterday, and we saw that Rutherford made 3 key observations in his alpha scattering experiment. Okay. And the first observation was that a greater percentage of the alpha particles pass through the gold for undeflected. The conclusion is that the atom is made up of a hollow sphere. Then smaller percentage, one out of about 2,000 alpha particles were deflected at wider angles. Okay, giving us an indication of the presence of electrons within or charges within the sphere. This gave us the idea of the presence of electrons within that almost hollow empty sphere. Then 1 out of about 20,000 alpha particles were deflected at back along the same path, indicating the presence of the nucleus, and then the nucleus almost having the entire mass of the atom, the nucleus being positively charged, okay, and the nucleus also being of greater mass than the alpha particles. Then he made his conclusion out of it. Out of these observations, we saw that, oh, okay, then the atom has the central core, which is the nucleus, and the nucleus is positively charged. This was not mentioned by J.D. Thomson. Okay. Now, the weaknesses, though the weaknesses are a lot, but one of the weaknesses is that he failed to talk about the stability of the atom. He failed to give us a planetary model of the atom. He failed to talk about the excitation and de-excitation of electrons. Okay. He also failed to talk about the emission of line spectrum, which I will discuss later. Then another scientist by name Niels Bohr picked what Rutherford also saw and then added quantum physics to it, and then created his own, also proposed his own model, which he termed as postulates. Okay, So Bohr picked on Rutherford's model and added quantum physics. Class, what is quantum physics? What is quantum physics? Anybody? Barack? Gansa?
Yes.
And what is quantum physics?
Quantum
Barack?
physics is, I think quantum physics is the study of the quantum realm.
Barack, you are right, but we have to simplify it for better understanding. Okay, somebody else is ready. Yes, let's hear from Esiedu.
Quantum physics is a branch of science that deals with the study of the universe, relating it to even the study of the tiniest particles such as atoms and molecules.
So yes, the study of particles that actually move at the speed of light. Tiny particles that actually move at the speed of light. Okay. So he added quantum physics to what Rutherford saw and then created his own view of his own model of the atom. Now, these were the findings made by Niels Bohr. So Bohr considered an electron of mass m orbiting around the nucleus. So an electron of mass m moving around the nucleus with a velocity v. Its speed is v, assuming the radius or the distance from the nucleus to the electron is r. Bohr saw that, yes, whenever a body is in circular motion, there is a certain force which enables the body in circular motion to stay within the circular path. What is the name given to this force? Whenever a body
force.
good. So whenever a body is in circular motion, the force which enables the body to stay within the circular path is known as the centripetal force. Centripetal force is actually a product of the mass of the body, the square of the body speed divided by the radius of the body. Okay. And Niels Bohr, through his analysis and experimentation, saw that this centripetal force, which enables the electron to stay within the circular path and wouldn't drop to hit the nucleus, is provided by that electrostatic force of attraction, between the electron and the nucleus. Force of attraction between the electron and the nucleus. So all that Bohr saw what provides the centripetal force which enables the electron to stay within the circular path. And he felt that so long as this force exists, the atom would always be stable. So long as that electrostatic force of attraction between the electron itself and the nucleus is there, the atom will be stable, Gideon.
So please, can you define the things?
Can I?
So please, can you define the M, G, and R? The R is radius. Please, can you define the M?
M is the mass of the electron. R is the distance between the nucleus at the center and the electron. And V is the speed. Okay. And so the centripetal force mv squared over r is equal to the electrostatic force of attraction between the electron and the nucleus. And he saw that so long as this force exists, the electron would always stay within the circular part and would not move spirally to crash the nucleus to disintegrate. Because remember, I said that last week, I said that Rutherford did not talk about stability. That because classical physicists had the view that the atom is not stable because whilst electrons move around the nucleus, it would emit radiation, okay, lose track and hit the nucleus to disintegrate. And Niels Bohr is saying that so long as this force, which provides the centripetal force, exists, the atom would always be stable because the electron will never lose energy and hit the nucleus. That is what he's saying. Please, are we okay? So that is Bohr's first postulate, his first observation. And his first observation discusses the stability of the atom or explains the stability of the atom. So Bohr's first postulate explains how stable an atom is. Then his second observation or postulate is that when you consider the wavelength of an orbiting electron, the wavelength of an orbiting electron is always equal to the circumference of the orbital. Electron is equal to the circumference of an orbiting orbital. The wavelength of particles, lambda, is provided by Planck's constant h.
Sir, please, what is wavelength?
I will explain, don't worry. Wavelength of an orbiting electron is equal to Planck's constant divided by the momentum of the electron. This can also be broken down as momentum is product of mass and velocity. So the momentum of the orbiting electron is equal to the mass of the electron and velocity. Okay. Now wavelength, Daniel, wavelength is the length between two successive. The issue is that at your level, you won't understand even when I explain because you haven't done waves. But when we talk about wavelength is a distance or a length between two successive crests and troughs. But my problem is that, Daniel, at your age or at your level, you will not understand it much. So as you grow, you understand some of these terms. Daniel, is that okay? Hello, Daniel.
Yes, sir.
So gradually you understand. So lambda, this symbol is what we are calling as wavelength. H is a constant. A constant is a fixed value. This is known as Planck's constant. Yasmin, are you there? Yasmin. Today the ladies, I hardly hear from them. Anita and the rest of you, only Ashima spoke some, and then Zena. The rest are all resting. And P is momentum. Momentum. Bohr is saying that the wavelength of the orbiting electron is equal to the circumference of the orbital. Please, the circle, K shell, L shell, M shell are the orbitals. They are also known as the stationary states. Stationary states or orbitals. Okay. Now, how do we determine or calculate the circumference of a circle? Zainab, how do we determine the circumference of a circle? Ashima, how do we calculate the circumference of a circle? Okay, Frank.
Sir, please, 2 pi r.
So the product of this, 2 pi r. So Bohr is saying that the wavelength, orbital wavelength, is equal to the circumference of the orbital. So 2 pi r is equal to orbital wavelength, which is h over mv. Now, class, help me make mv the subject. Help me make MVR from this equation. Help me make MVR the subject. Frank.
Sir, please, h over 2 pi.
H over 2 pi. This is Bohr's second postulate. Now, the product MVR is known as angular momentum. Angular momentum. So Bohr is saying that orbital angular momentum, this one, orbital angular momentum is equal to the integral multiple of Planck's constant. MVR is equal to a number n, a number multiple of the Planck's constant h over 2 pi. Orbital angular momentum is equal to an integral multiple of the Planck's constant. Don't forget, I said h is a constant. H has a value of 6.63 times 10 exponent negative 34. Okay, 34. And 2 pi is also a constant. 2 pi is equal to 6.6. Pi itself is 3.14284. Okay, so all that we are saying is that MVR, which is angular momentum, is equal to a number multiple of h, Planck's constant. Okay, that is Bohr's second postulate. So Bohr's second postulate is MVR is equal to h over 2 pi. And then the third postulate, Bohr's third postulate. Please, these are stuffs you must know and understand. Bohr's third postulate says that, yes, electrons are within the hollow sphere. So if this is the sphere, and you have the nucleus here, electrons are within the sphere, but they exist in a stationary state, or they exist in an orbital or in a shell. Electrons do not just stay in the sphere, but they exist in a stationary state or orbitals. Electrons exist in an orbital. Okay, and once they exist in an orbital, they can move from one shell to another, or one stationary state to another. Let's assume an electron is in K shell, n is equal to 1. This is n is equal to 2, L shell. Bohr is saying that electrons can be excited or be moved from one stationary state to another. And this is termed as excitation. Excitation. Let's define excitation. Excitation is a process whereby an electron can be moved from a lower energy level or stationary state to a higher energy level or stationary state. So it's a process whereby an electron is moved from a lower energy level to a higher energy level. Class, are you with me?
Yes, please.
So electrons can be excited, be moved from one energy level, a lower energy level, to a higher energy level, and that is excitation. Equally, electrons can also move from a higher energy level to a lower energy level. This is termed as de-excitation. De-excitation. So de-excitation, on the other hand, is a process whereby an electron is moved from a higher energy level to, hello?
So, sir, please, the excitation decreases the wavelength.
No, excitation decreases the it doesn't decrease the wavelength. But listen, understand that excitation is just moving an electron from a lower energy level to a higher energy level. Okay, so from lower energy level, so to some extent, it rather increases the energy of the electron, not the wavelength. Danny, are you okay?
Yes, please.
Excitation increases the energy level of the atom, because I'm saying that moving the atom from a lower energy level to a higher energy level, maybe from K shell to L shell, or L shell to M shell. And de-excitation is the process whereby an electron is moved from a higher energy level to a lower energy level. So it's the opposite of excitation. And that is Bohr's third postulate. So please, class, there are a lot of details about this, but as I said, at your level, I wouldn't go much into detail. You'll be totally confused. As you grow in physics, we'll be treating these topics. Please, are we okay?
Yes, please.
We are going to look at the evaluation, and we have less than 20 minutes to do this. So let me upload it to the page quickly, and then we wash our hands of this. Basi,
So if an electron moves up, like gets excited and moves to a higher energy level, is it that same electron that get de-excited?
yes. When an electron is excited, it becomes so unstable and can only exist in the higher energy level within a fraction of a second, and it must be de-excited. So it is that same electron. Are you okay?
Yes, thank you.
It is like you jumping to go up. When you raise your height, you cannot stay in the air, so you must fall. So it's similar to that situation. Are you okay?
Yes.
Okay, so please, I've uploaded this on a page. Let's all tap on it and open it, please. Tap on the link to open the page. Please, we need all to be included in this exercise. It's a very important exercise for we the Omegarians. So please, I expect 35 of you to open the link so we all follow suit. Have we all done that, please? Have we done that?
Sir, please, you have to
Yes,
do it right
please.
now.
Okay, so tap on it to open the link. I'm expecting 35 of you to be doing this. 35 of you. In fact, those of you who have actually opened, the number is not encouraging at all. I'm seeing 18 opening it. Please do that for us. It's a very important exercise for us. So let's start. So please be assured that all responses will be kept completely confidential. Okay. So be so open in whatever you're going to say about me, and do not cook stories. Let's be real. Links to joining the classes are shared before the scheduled start time. A, never shared before. B, sometimes shared late, often shared late. And D, always shared before time. So pick the one which is applicable to your physics facilitator, Mr. Ibia. 2, Does the teacher skip classes? A, skips class most of the time. B, skips class sometimes. And C, never skips class. So choose the one that you think is so applicable to me. 3, give the number of times the teacher has skipped classes from A0, 1, blah, 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 and E, up 4 and above. Please, are we on course? Class, are we there?
Yes, please. Yes, please.
Okay, 4. Teacher makes alternative arrangement if he or she is unable to attend classes. A, never makes any alternative arrangement. B, sometimes makes alternative arrangement. And C, has never skipped class. 5. Teacher is willing to answer your questions privately after lessons. A, never answers my questions. B, ignores my private questions. C, sometimes answers my private question. And D, always answers my private question. 6, are reasons given for not answering your questions privately. So A to D, read through and then let's do this quickly. Oh, the number is diminishing. Oh, 7, teacher's voice is very clear during class session. A, voice is always low. Voice is sometimes clear, other times not clear. Voice is most of the time clear. And D, voice is clear at all times throughout the lesson. 8, how clear are writings and illustrations on board and screens? A, handwriting is not clear. It is difficult to read. B, handwriting is sometimes not clear. And C, handwriting is clear at all times. 9, background of the teacher during lessons is A, always noisy and disruptive. B, sometimes noisy. C, always quiet throughout the lesson. I've even not observed my background. Is it usually noisy, class? Is the background usually noisy?
No, sir.
I've not taken a note of this. So 10, the teacher gives assignment on topics taught. A, never gives assignment. B, occasionally gives assignment. C, often gives assignment. And D, always gives assignment. 11, teacher marks assignment promptly and gives feedback for improvement. 11, so A, never. B, never marks assignment given. B, occasionally marks assignment given. C, marks some and leave others. And D, always marks and gives feedback for improvement. I think one must also be designed for us to assess our students individually. 12, how many exercises, tests, assignment, homeworks, or group works have been given by the teacher? So look at A to F and then pick a figure. Kingsley, your background is noisy and now, not all the time though, by now. 13, my level of understanding of what is taught is A, I do not understand most of the time. B, I understand some of the concepts. C, I understand most of the concepts. And D, I have excellent understanding of all concepts. So please, this is to the individual's level of understanding. 14. Are videos of lessons shared with you? A. Never. B. Sometimes. And then C. Shares videos on all lessons. "15. Rate the stability of teachers' internet connectivity. Connectivity is always bad. Network drops too frequently. Network drops occasionally. Network is consistently stable throughout the lesson. 16. The method used in the lesson delivery is less interactive, quite interactive, very interactive, excellently interactive. 17. Hey, people are going, oh. I had 33 of you, now it's 27. Would you like to maintain your teacher? A. No, I wish I have a different teacher. B. Maybe. C. Yes, I will always like him or her to teach me. Next time, we should always also be given. Would you like to maintain your student? Then I also answer. 18. 18. I will join Omega vacation classes in my next vacation holidays. A. No, I will not join Omega. B. Yes, I'm not sure I will join Omega. And C. Yes, I will definitely join Omega. Here, the answer must be that yes, I will definitely join Omega because I also wish to maintain my students. 19. Did the teacher meet your expectations? A. No, my expectations were not met at all. B. Yes, my expectations were somehow met. C. Yes, my expectations were met to a large extent. And yes, my expectations were excellently met. 20. Any other comments about the teacher? Over to you. You like it. This is over to you, students. So please quickly fill this column and let's get to the last one and we submit. Any other comments about the teacher? Then we have any other comment for Omega management. Let's fill the two quickly and submit. When you fill and then you don't submit, place is cos 90, whose magnitude is equal to
0.
0. So please, when you finish, submit it. Just tap on submit so that we don't do a cos 90 job. Are we done? Class, are we done?
A few more
Avelina?
minutes.
Okay.
A few more minutes.
Yasmin, Elitia Nanakumi, Anita, Ashima, Esiedu, Augustine, Barak, Blessing, Daniel, Ernest, Frank. I'm going individually. I've lost track of you people. Frempoma, Gideon Isaac, Isabella Jackson, Kennedy, Joshua, Martin, Morris, Michaela, Ohene, Blessing, I called you today. Blessing, I called you to bless you.
I responded. But then I responded with
okay.
my name Otokuno
Okay.
on the laptop.
Yes. Ohene, Paddy, Yasmin, Zaratu, Zainab. Zainab is gone. So as I said, if you finish, just hit on the submit to bring finality to all that you have done. Else, cause 90, which is a no answer. Have we all finished? Or you are still writing something for about the teacher or for mega management? Okay, so while you do that, please, next week, Tuesday, there will be a test. Just fill in, okay? I want to put together few questions on all that we've done, not so detailed, fill in, so as to test conceptual understanding. And that will be done on Tuesday. So please get yourselves prepared. Class, is that okay? Are we okay?
Yes, please.
All right. So if you have submitted and there is no question, then we call it a day. If you have any question, quickly ask. Well, we have about 4 minutes to go. Is there any question? From archaeology to anthropology. Frank. All right. So if there is no question, then I think this is where we end today's session. Thanks so much for your patience, your contribution, and the presence and everything. Okay. Please make time to revise, because the test is a must one, which we have to answer. So we'll continue on this week. May the good Lord take care of you and protect you. Frank.
Please, the test is when?
Oh, basically all that we've done, from mirrors, spherical mirrors, refraction lenses. So just fill in to test your understanding of all that we've done. Not so detailed, okay? So just get
Please,
yourself
I
prepared
mean,
for
like, which day?
on Tuesday. It will be on Tuesday.
Okay, sir.
All right. Okay, bye-bye then.
Bye.
All right.
Bye.
Bye-bye.
Bye, excellent.
Bye-bye.